Hello friends, in today's question, a rod AB of mass m and length L is lying on a horizontal frictionless surface. A particle of mass m traveling along the surface hits the end A of the rod with the velocity v0 in the direction perpendicular to AB. The collision is elastic. After the collision, the particle comes to rest. So we have to find out four things. Find the ratio of, you can say, small m to capital M. Part B, a point P on the rod is rest immediately after the collision. Find the distance AP. And C part, find the linear speed of the point P at a time pi L 3 v0 after the collision. So in this case, we are given that there is a vertical rod which is lying, or rather we can say there is a rod which is lying on a horizontal surface. So let us suppose this is a rod and the length of the rod is given as L. So this is length of the rod, and we have this point, let us suppose is B, and this point is A, and it says that a particle of mass m hits the end A. So let us suppose there is a particle, this particle, who is having a mass m, and this rod is having a mass of capital M. So this particle is moving with the velocity v0. In the first case, we have to suppose to find out what will the ratio of small m to capital M. So we assume let this C is the center of mass of this rod. Therefore, we are going to get this will be our L by 2, and this portion will be our L by 2. Now, after the, you can say, collision, it is given that the particle comes to rest, and this rod is obviously going to rotate about the center of axis, and also it is going to move in the forward direction with the velocity, we can say, let us suppose that velocity is given as v. So this rod after the collision is going to have two types of motion. One will be rotational and another will be translational. So let us draw it. So after collision, this is the center of mass, we have B, this is A, and this is our mass M, and it is at rest after the collision. And we say the center of mass, this rod is moving with this rod is moving in the translation motion with the velocity v, and there will be a rotational motion, and we say that the moving with the angular frequency of omega. So we have, this will be our before collision, and this we are going to have after collision. So mass is capital M, so this will be our L by 2, and this will be our L by 2. So after collision, we consider that this velocity of the center of mass is v, and it is rotating with a, you can say, angular velocity of omega, and C is the center of mass. So let me write it here. C is our center of mass. So we say let V is the velocity of C, that is center of mass, and omega, its angular velocity after collision. So the table is given as frictionless, so we can use the conservation. So let us start with the conservation of linear momentum. Conservation of linear momentum. Initial momentum will be equal to final momentum. So initially the rod was at rest, only the particle was moving, so initial momentum will be equal to mv0, and the final momentum, the mass, you can say the particle is at rest, only the rod is moving with the velocity v. So we get m times v. So let us call this as equation number 1. Now conservation of linear momentum. Conservation of angular momentum now. Angular momentum. So we can write initial angular momentum will be equal to final angular momentum. Initial angular momentum is equal to final angular momentum. So initially let us suppose given as Li and final is given as Lf. So you can find out, or we can write that our Li will be equal to mv0 L by 2, and we have our L final will be equal to the moment of inertia about the center of mass and its angular velocity, and we get this as ml square upon 12 multiplied by omega. So equating these two equations, we can write that our mv0 L by 2 will be equal to ml square divided by 12, and this is our omega. So this goes by square and this cancels by 6. So therefore we can write that mv0 will be equal to m omega L divided by 6. Let us call this equation number 2. Now we can use conservation of energy, or we can say kinetic energy. conservation of kinetic energy. Initial kinetic energy will be equal to final kinetic energy. Initial kinetic energy will be equal to final kinetic energy, and initial, let us suppose, is written as KEI, and final is our KEF. So we can write that our KEI, kinetic energy initial, will be equal to, because only particle is moving, so we get half m v naught square, and kinetic energy final will be combination of both the translational as well as rotational, so we get this as half m v square plus half IC omega square, and this will be capital M. So we already know, or let's equate it first and then solve it further. So we can write this as half m v naught square is equal to half capital M v square plus half, we know IC is our ml square upon 12 multiplied by omega square. So this half cancels out throughout, so we get that m v naught square is equal to capital M v square plus m L square upon 12, and we have omega square. Let us call this equation number 3. So we have 3 equations. So first of all, we are going to use equation number 1 and 2. Okay. So let me write here once again. Equation number 3 is already here. So we have equation number 1 was our m v naught is equal to m times v, and second was our m v naught is equal to m omega L upon 6. So this was our first equation and this was our second equation. So using first and second, left side is equal, so right side will be also equal. So you can say from equation 1 and 2, from equation 1 and 2, we get mv is equal to m omega L divided by 6, and from here m cancels with m, therefore we get that our v is equal to omega L divided by 6. V is equal to omega L divided by 6, and also we can find out our v naught. So we can say that our v naught will be equal to m divided by small m and multiply by omega L divided by 6. So we found out v and v naught, and therefore we are going to use equation number 3 now. And equation number 3 is, we are taking m common from equation number 3 on the right side and taking it ratio to the left side. So we say from equation 3 we get m upon capital M, and this becomes v square upon v naught square plus we have here L square omega square divided by 12 and V naught square. We substitute the value of V as well as V naught. So therefore, we can write that M upon capital M will be equal to, our V was omega L by 6. So this comes as omega square L square divided by 36 multiplied by, and we have V naught square. V naught square was our M upon small m multiplied by, and this also is square. So this also becomes omega square L square divided by 36 plus L square omega square divided by 12 multiplied by V naught square, and that is equal to M square small m square multiplied by omega square L square, and we have here 36, and 36 cancel with 36, omega square this goes away, and here also this goes away, and this comes as 3. Therefore, we can write that our M upon capital M will be equal to M square upon capital M square plus, this comes as 3 M square upon capital M square. So this will be equal to 4 M square upon capital M square. And so it's quite simple now. So this implies that, let me write it here, M upon capital M is equal to 4 M square upon capital M square. From here we can say that, so this comes equal to, we have to find out ratio of, ratio of small upon capital M. So this gives us that M upon capital M is equal to 1 by 4. So this is the ratio of part A. This is our part A. Ratio of small particle mass to the rod mass is 1 by 4. Now we are going to find out, we can say, part B, and it states that a point P on the rod is at rest immediately after the collision. Find the distance AP. So we are going to find out part B. So let us draw the rod. So this is our rod, point A, point B, and this is the center of mass, which was moving with the velocity v, and it is rotating with the angular velocity of omega, and it says that a point P, so let us suppose this is point P, and it is at a distance of x from the center of mass C, and it is given in the question that this point P comes immediately to rest after the collision. Okay. We can write here point P comes to rest immediately after the collision. After the collision. So this point P is going to have two types of motion. One will be the translational and other one will be the rotational. Okay, so let me draw it without the rod. So this is our center of mass C and this is our point P. So it is going to rotate in this direction with angular velocity, and as the rod is moving forward, this P point will also try to move in this direction, let us suppose with the velocity of Vy. So you can say point P will have two types of motion. Point P will have two types of motion. Two types of motion, translational as well as rotational. Translational motion and rotational motion. So it means the velocity at point P will be determined by translational motion as well as rotational motion. So you can say that velocity of point P is determined by translational velocity, which will be because of translational motion, and you can say rotational motion is going to provide the rotational velocity. Okay. So let us say rotational velocity, translational velocity first of all. Translational velocity, and which will be velocity of center of mass. Velocity of center of mass, which is given as V. Therefore, we can say that V translational, V trans will be equal to velocity of center of mass, and the rotational velocity will be depending upon the angular velocity omega and the position of point P with respect to center of mass. So you can say that rotational velocity will depend upon angular velocity omega, and position of point P with respect to center of mass, and position of point P with respect to center of mass, which is denoted as C. So we can write that the velocity of point P with respect to the center of mass, therefore velocity of point P with respect to center of mass will be equal to omega multiplied by position of point P with respect to center of mass. And we already said that this is our x. So position of point P with respect to center of mass is our x. And we can also write it here that this is our position vector of point P with respect to center of mass. Position of position vector I should have written. Position vector of point P with respect to center of mass. And we have already denoted in figure that position vector of point P with respect to center of mass is equal to x. Therefore, velocity rotational, that is v ROT, will be equal to omega times x. And it is given that this point is at rest. Okay, in the question itself it is given that the point P on the rest is at rest immediately after the collision. Okay, so it means if the point P is at rest, the summation of both the rotational velocity as well as translational velocity should be equal to 0. So the point P is at rest immediately after the collision. After the collision. Therefore, V translational plus V rotational will be equal to 0. So we get V translational is equal to V plus omega x is equal to 0. So therefore we get that V is equal to minus omega x. So it means it is in the opposite direction. Okay, and we have to suppose to find out the distance also. So it means we have to find out x also. So we can draw this will be in opposite direction. So this is our center of mass. This is point P. So we are going to have this will be our V translational and this will be our V rotational. It is rotating in this direction with the angular velocity omega, whereas the center of mass is moving in this direction. So both will be opposite. So from here we can say that our x is equal to minus V upon omega, and we can find out our V. V is our V naught was equal to capital M divided by small m multiplied by V, and we already found out that from here we can say that V is equal to small m capital M multiplied by V naught, and small m upon capital M is equal to 1 by 4. So V is equal to V naught divided by 4. And omega we can also find out. So let me write it here. So we can see omega is equal to, we already know the equation, and we can put m upon capital M 6 V naught upon L. So m upon capital M is 1 by 4. So this becomes 1 by 4, and we have 6 V0 upon L. So therefore we get omega is equal to, this will be our 3 by 2 V0 upon L. So we got omega as well as V. In terms of V0, we are going to substitute it here. So I can write, therefore x is equal to minus, this is our V0 upon 4 multiply by, we get this as, where is, yeah, here it is. This is our 1 upon 3 by 2 V0 upon L. So V0 and V0 goes away, and we can write this as 3 and this is 2. So we get this as minus L by 6. So we got that our x, that the distance of point P, x is equal to minus L by 6. So this is distance of point P. Yeah, we have to find out AP. Sorry, this is only x. We only found out this is our x. Okay, but A is somewhere here, so we have to find out AP. Okay, and let me, here the only difference is that because of this negative sign, okay, so we can write this negative sign presents that the point P is at the opposite side. So we are only interested in magnitude. So let me write it here. The negative sign shows that point P is on the opposite side. On the opposite side. So this is the only significance of this minus negative sign. So we can say x is equal to L by 6. So we are interested in AP. So we know that the distance of point A from the center of mass is L by 2. So AP will be equal to L by 2 plus x, and x we found out is L by 6. So we can say AP will be equal to L by 2 plus x, and that comes as L by 2 plus L by 6. So we get AP will be equal to 2L by 3. And we are now in the last part. We have to find out the linear speed of point P at a time pi L 3 V0 after the collision. Okay. So we have to find out now the velocity of linear speed of point P. Okay. Therefore, part C. So we already found out the value of V as well as omega. Okay. So we can see just after collision, we know that V is equal to V0 upon 4 and omega is equal to 3 by 2 V0 upon L. We are going to find out that at time t is equal to pi L by 3 V0, what will be the rotation in the rod. So we can say after time t is equal to pi L upon 3 V naught, the angle through which the rod rotates, is, let us suppose, is given as theta. Theta will be equal to omega times t, where t is the time period, omega we already calculated, so this becomes 3 by 2, and we have V naught divided by L multiplied by pi, and this becomes 3 V naught. Length cancels out, 3 V naught also cancels out, so we get theta is equal to pi by 2. So it means there will be a rotation of 90 degree. So at time t, the rod will be at an angle of 90 degree with respect to the previous position. So the previous position which we have assumed is a vertical rod, something like this, and this was our point P, this was center of mass, this was our B and A, and this was our mass M. So when it is going to rotate by 90 degree, so this will be the final position at time t. So this will be the center of mass, and this will be point P, this is A, and this is our B, and the velocity was in this direction and rotating angularly this way. So now we are going to have the center of mass, this is point C, it is going to have a velocity V in this direction, and rotation will be still in angular in this direction. Okay, so therefore here this is point P, and we are supposed to find out the linear speed of point P. So point P is going to have two components. One will be because of the translational motion of the center of mass, and another one will be the rotational, which is perpendicular to the rod. So we can say point P has two velocity components. First will be, once again, due to translational motion of center of mass, due to translational motion of center of mass, and second will be rotational, which is perpendicular to the rod. So we can write that our velocity of point P is going to have velocity translational plus velocity rotational. So translational is we already know is our velocity of center of mass. So this becomes velocity of center of mass plus rotational will be the angular velocity multiplied by the position vector of point P with respect to center of mass. So it is almost finished now, and velocity of center of mass will be our V0 4 in I direction, plus we have omega we already calculated, this is our 3 by 2 V0 divided by L, and this is in K direction multiplied by the radius vector, position vector of P, which is in negative I direction, so this will be equal to L by 4, and we have this as I. So this L cancels with L, and sorry, here it is 6, my mistake, and 3 cancel with this, we get 2. So therefore we can write that our this is equal to V0 upon 4I, and this is our, this is, 1 second, yeah, so this is our omega cross R position vector of P point with respect to center of mass. So we have here K cross negative of I, so this will be giving us a V0 upon 4 times J. So we are only interested in magnitude, so we can say that Vp is equal to V0 4 whole square plus V0 4 whole square and its square root. Taking V0 as common, so this becomes as 1 by 16 plus 1 by 16. So we get that velocity, linear velocity of point P will be equal to V0, and this will be our 2 square root of 2. So this is the linear velocity of point P. This is the linear velocity of point P at time t is equal to pi L divided by 3V0 after the collision. After the collision. So this completes the question. Thank you.